Yes.
Okay. Okay. So yeah, thank you for the invitation. Yeah, today I want to talk a little bit about our recent work, Platonic representation of foundation machine learning interatomic potentials. So to begin with, I'm not sure if you are familiar with representation or embedding. I guess so, but I still want to share that the definition that I think for embedding is it is a numerical vector that captures the features the model has learned about the environment. For example, if we look at the word water, so in the machine learned representation, it's not the letters, like it's not WATR, it's actually a rich internal concept that captures everything or that every concept that has correlation with water, and it can be liquid or can be related with transparent, or it's very essential for life. So but in the model it uses a vector to capture this very rich concept. And then for materials, usually we represent the materials with as a graph. And then for the graph, we have the node and also the edge, which is the bond between different atoms. And then we also use the lattice to represent the environment that all the atoms are in. And then I for developing the or training different machine learning interatomic potentials, we need to have some kind of architecture, and this is part of the architecture I take from the NetQuip model. And as we can see here, for representing the materials, we have the node to represent the atoms, and then within the cutoff, we take the different, like the age or the bonding between the different atoms. And then because in NetQuip model, they use the message parsing, so there are message parsing interaction between the different blocks. But for every like every information learned by the model, for example, of the nodes, with the embedding are also represented as vectors. So this means the information of the materials flows in the model as vectors. And then this lead to one question, that what is a high quality embedding, right? So for in the LMs, we know that if the LM can learn quite well about the semantics, then we can do some arithmetic. Like if we have the embedding of the king minus the embedding of a man, and then plus the embedding of a woman, then we will get the embedding of the queen. So in materials, in material science, when we train the model, we also want to evaluate the quality of the embedding. One very straightforward way is to check how well the clustering of the learned embedding, because when the elements comes from when the elements have very similar chemical properties, they tend to cluster together. And here is one of the example taken from our plotted embedding from the maze media model. But there are also other ways to evaluate the latent representation that has been learned by the models. The clustering I have mentioned, but for clustering specifically, we can also check how well the clustered has how well the cluster has been learned. For example, even on this very simple task of the MNIST dataset, we want to differentiate the 10 different digits from 0 to 9. But if we have two models, like on the model B or model D, even though they can both work on this task, but we can see clearly here that on model D, the clustering is not so well. There's some very blurred boundary or very vague differentiation between the different clusters. So clustering is one of the important metric for evaluating the latent representation. And another aspect is the compression, which is, for example, if we have two VAE models and we have the bottleneck of them, but if we try to train the models to work on the same task, but if your model only have 8 dimensions in the bottleneck, but I have to use 64 dimensions to achieve the same performance, then this means your model is well trained and the compression of information is much better than my model. So another aspect that is very important is the disentanglement. So for disentanglement, I think it appears much more important because when different models we try to build the multi-modality models, we want to disentangle the different features, though the different modality, the contribution from them to the data can be evaluated. For example, for human beings, if a model can disentangle the features of the skin color from the age or their gender, then this model can be more steerable for our purpose. Is there any questions? I didn't see the.
Yes, I have a question.
Yeah.
So if you can go back to the previous slide, please.
Yeah, this one.
Yeah, so here, for instance, for clustering, do we have a clear sense of, like, for instance, for materials clustering with respect to what we're looking for? Because I guess we can like have clustering based on many different things, right? And are we like trying to cluster through everything, or like how do we essentially evaluate a good latent representation for a specific case?
Yeah, so for in my work, because yeah, we do have different ways, like we can use only k-means, that is unsupervised way to cluster the points together. But here, because they are labeled, yeah, because every atom is labeled, right? So for every embedding, I already know who they are. So now I can plot them together and then only evaluate like the carbon group, and to check the mean distance between the different points. And then so because the distance is kind of the uh, closeness of different points, so this can be one metric that can be used to evaluate the clustering of them. Is that clear?
Yeah, but I guess like for instance here the task is like try to see if they can cluster based on composition family, right?
Yeah.
But what if like for instance you're trying to cluster them, I don't know, like say using the space group for instance, or like just the geometry of the structure. Is that like another way to evaluate
Yeah,
the
yeah, definitely.
embeddings? And like is that for instance like here we see them clustered by chemical composition?
Yeah.
How do we do to evaluate, for instance, whether there's like another internal clustering based on another category? Not sure if the question makes sense.
Yeah, I think that makes great sense because because here they are labeled, but if they are not labeled, so we have to use unsupervised way to cluster them, and then for that, they can recognize, like if I don't label the the brown part or the orange parts as clustered. But if you use another clustering method that can recognize this part, and then we can try to check if the points are actually meaningful.
Okay,
Yeah.
I see. And so that's what you're gonna look at, right?
Yeah, but here, because they are all already labeled, so I only checked the clustering, like the compactness of them.
Okay, thank you.
Yeah. 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 So the learned embeddings are actually the knowledge mapping of the model that the model has learned. So yeah, then comes to why we care about this Platonic representation. So the Platonic representation actually comes from Plato's the story that Plato imagined an ideal reality, that our observations are mere shadows of that, which means, so when we are in a cave, we try to understand the environment around us, but we don't have any knowledge outside. So when we try to perceive the world, then it only based on the shadows, which is from the outside. If we can go outside of the cave, and then which means we have more data or more observation of the world, and then we can construct a better understanding of the reality. So based on this, the team from MIT in 2024, and they published this paper, the Platonic representation hypothesis. On their paper, the hypothesis says that different neural networks, or they are trained with different objectives on different training data, different training data, and also different modality. For example, here, even though they are trained on the text, or they are trained on the images, but all they are learned, or the learn, or they are latent space or latent information are converging to a statistical model of reality in their representation spaces. So inspired by this, we are wondering if in materials, in the models trained for materials, can also having this property. That's the motivation of this work. And then in parallel to our work, only after we published our archive, and there are several other, almost simultaneously, several other works appear, and they also try to look at this problem in different angle. For example, this one from Raphael's group in MIT, and they look at over 60 different models, including the machine learning interatomic potential, but also they check the GPT model, or the language models, or even the generative models. And then their conclusion is that all the models are universally converging, but because this is only very statistical way to look at the different models, latent space, and also the latent space is not aligned. So there might be some misunderstanding here, but still the conclusion is there. And then this is the work from MLIPs group and also Sangyu Chun. And they try to look at the embedding space at the local level. So this is the general level, and this is look at them in the local level. And their conclusion is that their representations learned is not converging, but this is also like one aspect that we need to align the latent space first to compare them. Otherwise, if we rely on like the angle dependent similarity, then because they're not aligned, there might be some misleading results. And this one is from the mathematics background. They try to give a proof of the perfect Platonic representation, like from the architectural aspect of training the different models, and how the Platonic representation will appear, and when they will be broken. So for us, we want to check.
A question regarding all of these works. Do we know how sensitive these alignments are to the data sets we give them? Or are they like mostly studying alignment based on model architecture?
Yeah, so for the previous, for these two and including mine, we didn't touch too much on the influence of the training data set, even though I also have some discussion I will introduce later in the results part. But in this one, it does check like some of the architectural choices, like the training data set or the different setting of the gradient descent. Yeah, that will influence the appearance of the Platonic representation organization.
Thank you.
But because this one is very mathematical, so I also don't not so crystal clear about the details.
Okay.
So our purpose is try to check if this Platonic representation can appear in the machine learning interatomic potentials. So everyone is very familiar with what is in a machine learning interatomic potential. Is so it's kind of we use deep neural networks with a lot of the engineering choices. For example, the Euclidean choices, conservation constraints, or we can choose message passing, and we can also design different loss functions to regulate the behavior of how the model learns the information. But all in all, we for learning and machine learning atomic potential, we use the deep neural network, and then with the representation of the structure, and we can build a function that can map this structure with the energy. And then for the force field, then the forces are the negative derivative of the energy to each atomic sites. And then we can also have the stress there. So I summarized the three different flavors, but there might be more. So based on my understanding, one is the representative is the NetQuip model, because they, including NetQuip model or 7net model, they all use the message passing. But for message passing is quite computationally demanding, and then for these maze-based models, they use this atomic cluster expansion. But all of these two are all graph-based. They are graph-based. And then this UPET, now I think they changed their name, but for the initially the PETMAN model, they are based on the transformers. So for graph-based models, one limitation is that the long distance interaction cannot be well captured. But for transformers, because it's global attention, so they can capture the longer interaction. And then, we do have a zoo of the machine learning interatomic potentials, and of course, the on the Met bench, the ranking can change from time to time, and we already have a lot of models to choose from. But no matter how they try to claim like the different accuracy or different F1 score to rank the models, what we care about as the material scientists is that what kind of chemical and physical information the model has encoded or the model has learned, because that limits the accuracy of the model to our system. So so try to answer the question if the representation in different machine learning interatomic potentials are aligned or not. So first, we try to extract the representations. Here we choose 7 different models because we want to check the equivalent models and non-equivalent models, which we choose the op models. And fortunately, in op models, they also trained the conservative model and also the not conservative, the direct model, they call it. So this provides us a very good set of models that we can compare them. And then we plotted their representation with PCA in the, here is in 2 dimensions, but we can easily go to different dimensions. And then we look at their original representation. And as we can see, their original representation is not so comparable, which is in different aspects. For example, for the math models, here we only extract the invariant part, and they are 128 dimension. But for op models, in their default setting, they are 256 dimension. So if we want to compare them directly, which is not mathematically so straightforward, So the different appearance of the representation of the different models comes from three different ways. One is the model that they are training depends strongly on their training setup. For example, they have different architecture, different design of the loss function, or they even have some very random initialization that are different. And also we can see we couldn't find any invariance, even though the two op models appear to be quite similar. But with the other models, we couldn't see any invariance between them. And the core reason we think is if all the models can be aligned, so they should be comparable. And then what we want to check is if we change, because now all the models are in the arbitrary coordinate system. And then so what we think is we want to put them in one coordinate system. That's why we try to think in different in these four aspects. One is our construction of that coordinate system. It should be model agnostic, and so it's not dependent on any model. And then then the way of our transformation should respect the true geometric correlations of the different embeddings in the model. And then also we should offer sufficient dimensional diversity that can represent that the representation spans the chemical space broadly enough to resolve the chemically distinct environments, which is the dimensionality of the coordinate system. And then the method should be robust, so the representation extracted shouldn't change a lot, like due to different random seeds or the permutation of the anchors. So the way we try to construct this unified representation space is to use the anchor-based projection. So the anchors are the other points that we sampled in all the embeddings we care about. And then for example, here, if we only care about 3 anchors, and then we choose the 3 anchors, and then the yellow one is the target anchor, and then we compute the cosine similarity, because for cosine similarity, it can best preserve the angled correlation of the different embeddings. And then the 3 anchors defined a new coordinate system, and so now all the points are projected into this space. So what's important here is the number of anchors and also the way how we sample these anchors. So the way we sample the anchors, we compare the random sampling and also the direct sampling. Direct sampling is developed by Shipion's group when they try to develop the ChargeNet force field, and then they develop this way, this one. So for the different number of anchors, here we choose, this is one illustration of 100 anchor points and their distribution on top of the entire chemical space. And we can see the diversity of them is quite good. So yeah, with this kind of transformation, anchor-based transformation, we can see that the 7 models, their representation started to converge, and they are quite aligned. So, yeah.
So, like in the beginning, they were not. I mean, how do we compare like the different PCA of the different models? Because is it that, are we supposed to see them have the same, or no? Is our PCA supposed to be aligned if you compare different models? Is that how we decide whether the representations are aligned, or is there like a metric that you measure?
Yeah, so here, because they're clearly not aligned, right? Like from the mass large model and the mass medium model, even though they have very similar architecture and only the numeric accuracy is different, right? But like if even the mass large, medium, and small model, their representation is like arbitrarily rotated or even arranged, like in
Okay,
space. Let's think about them as one molecule. So this molecule can rotate and in different angles. So it's if we don't figure out one way to align them, so the model will recognize them as different molecule, right? So it's
but I
still
guess the question is, how do we decide if they're aligned? Is it that they're supposed to, once we project them in their principal component, have the same range or the same kind of values? Or
yeah. So this is
like, for
only
instance,
this is only from appearance, right? Like the chemical species are starting like the gray ones are the transitional metals. So the arrangement are starting to converge, but we also have the statistical way to like the statistical metrics to calculate their alignment.
I guess the point here, maybe, are you trying to say that if we pick some of these anchor points, relative to them, we see the same patterns emerging? As in, like, I don't know, for instance, if you have this anchor point, for all of the models, the distance or the angles between these two are supposed to be the same.
Yeah. If they are converging, right, to the Platonic representation.
And there's a question, actually, it's a good question in the chat, is, are the PCA's axes shared? Or are you like just projecting the, recomputing the new PCA axis for every model?
So for the Platonic representation, they are shared because they are in one unified space, so they can be shared. But for different models, they couldn't be shared because the dimensionality are different. We cannot use one shared PCA system to plot them, right? Plot the different embeddings from different models.
So for the maze ones, you share the same axis, and for the
So for the math one, because for the math one, they are all 128 dimension. The we can share the uh, the principal uh, axis, right? But even though we share them, but because they're in different, they're in arbitrary rotation, right? And arbitrary um, appearance in the system, in the coordinate system. So we couldn't align them, even though we used the shared one. But here for the Platonic ones, we all use the shared PCA axis.
okay,
Yeah.
okay,
Yeah. Yeah, we also checked the number of different anchors. So we checked the anchor from 3 to 400. And then even though only with 3 anchors, we can start to see the alignment of them, which means the different models, they are indeed converging uh, to one representation. But if that's the Platonic representation or not, depends on how well uh, like the correlations or the information can be captured by the coordinate system, because we only have 3 dimensions, which means a lot of information are quite folded into like the one dimension or another dimension. That's why we want to increase the number of the anchors so we can unfold as many correlation between all the embeddings as possible. And then we start to observe that from anchor equal 100 to 200 and 400, all the embeddings are kind of becoming stable and they didn't change a lot. So that's why we think 100 might be the dimensionality that can help us to capture the Platonic representation that can also unfold all the correlations between different embeddings. Yeah, so for the methods, we try to sample the different anchors. We compared the random sampling and also the direct sampling. There are also other sampling methods like the furthest point, but here we only compared these two, and we find that because we couldn't judge all the clustering or the quality of the representation based on their appearance. So that's why we use the k-means to check the clusterability and also the COHAS score to check if the points are far away from each other or not. So based on these two metrics, we find that direct sampling can indeed offer better clustering of the representation space. So that's why we use the direct sampling rather than the random sampling.
I have a question.
Yeah.
So for clustering, I mean, here, because we have the labels, we can kind of see that there is a clustering. But related to like the previous discussion, I feel like if we didn't know the label in advance, it would look like one huge cluster, right?
But actually, because this is only in 2D, so everything is like a flattened, right? But in higher dimension, it's kind of a volume or a cloud. So for this cloud, then if we use clustering methods, we can still recognize part of this organization of the different atoms, but they cannot be as accurate as the labeled ones, right?
And another question I have is, do you think that all of these models, they converge to kind of the same representation once we pick enough anchor points because of the energy differences they're fitting to? Like, because they're learning the different energy of the points relative to each other, right? So because the models are accurate in predicting the energy value of one point, they're gonna have the latent space adapt to this, right? So they're gonna have two different points be, I don't know, spaced by this much because their energy difference is also supposed to be spaced by this much. And then once we align this latent space to the same anchor point, we kind of find the same representation again.
Yeah, exactly. Yeah, and this is also quite similar, quite close to one of our observation that whether this kind of arrangement is determined by only the training data set or determined by the physics that the model has learned. Yeah, so we find that it's the latter one, at least mostly the latter one dominates this kind of organization or this kind of representation. But still, the training data set can also play a role because, as we can see here, for the 7 OMAD model and the mass OMAD model, and they kind of the representation is not so well like aligned to the other models, and also they are more like the squeezed together. So this is kind of because of the larger training data set, because OMAD is much larger than the MP data set.
So okay, so the point is that it aligns more to the training data set, right? Like based on the training data set, we do see the same alignment. If we change the training data set, it might be different.
Yeah, but still, like if we don't look at them so strictly, but still, even though they have different training data sets, they still can be aligned. Like the orange part is still aligned, but maybe in this two-dimensional way, we look at them, they're like the squeezed. But internally, we have the statistical metrics to check their similarity. So we can prove that they are actually aligned.
And is that just to go back to the goal? Is it that if we can prove that the different representations can be aligned in a given referential, what does this help us do? What does it mean?
Yeah, I will introduce what this can be used for.
Okay.
Yeah, but I will skip this one because this is quite straightforward, that the different Platonic representation can still preserve the periodic properties of the different elements, which means our transformation doesn't disrupt the chemical information learned by the model. And here we use the quantitative evaluation for this alignment. So for this Procure state scores, which is used to measure like the global, like the topological distribution, like the different clouds I have shown before. So they can be used to evaluate how the clouds are similar or not. So as we can see, all the colors are nearly towards the red part of the red color, which is one means they are exactly the same. And then, yeah, and all of these values are above 0.5, which means all the models are actually in their topological sense. The distribution of them are aligned. So this is one illustration of how this works. Like if we have two representation, which is the blue one and also the red one, and we try to check if their topological distribution are similar or not, then we can use this Procure state score to measure that. And then this is also a very strong proof for that all the models are actually learned to organize the chemical information in a quite similar way, which is the reason why we can see this Platonic organization of all the embeddings. But yeah, one thing we also found is locally, like if we have the check the local, like the local environment or the neighbors for different embeddings in the embedding space, and then we use this mutual k nearest the neighbor, this score, to check them, and we found that even though the model globally the topological distribution are similar, but actually like each point or each embedding are actually not so similar, like their similarity is not that high. This led to one of the reason for our next in our one of our application, that if we try to use the different model to capture the difference of different polymorphs, because polymorphs are globally they are similar, right? But I mean some polymorph, like if they have the distortion or different connectivity, and then for different polymorphs, the models could not capture their difference so well. This is because locally their embeddings are still not aligned. They are still different. Means the model still learns slightly different or actually different exact embeddings for the different for the same, even for the same atoms from the same material. And then this optical transport is used to check if we want to change, like if we have two distributions, and how much does it cost from to change map one distribution to another one. And then so the cost, the lower cost means the model are more similar because they can easily map to each other. And we found that so all the mass models, the cost is quite low, but when the models are we try to transform the model from the distribution of models from mass model, which is trained on MPTRH, to the OMED based models, the cost increased, which means there's influence from the training data set. And then we have this super score to organize the three parts of the information together. Which is expressed as this way because the optimal transport is kind of the energy cost. So that's why we have this exponential part. But this CPU score is bounded between 0 to 1. So we hope in the future, if people try to check the similarity of embeddings learned by different models, then the CPU score can be used. Yeah, so here comes the application. So even though all the models are aligned, so what we can do with this property. So one of the property of aligned representations in the computer science or in machine learning is we can do the model stitch. So this can be more useful if we have two models that are trained by at different modality. For example, we have this model trained with text and the other model trained with the imaging, and then we can stitch them together as long as their representation space are aligned. And then if we input the text, and then we can output the imaging of them. But we don't train the machine learning stitch the interatomic potentials together, but we do have examples or evidence that for the interatomic potential systems, this kind of stitching behavior can also work. So first we want to
I have a question. So you're saying that stitching is useful if you have, for instance, image and text. Is it like you're stitching on the encoder of one with the decoder of something else? Or?
Yeah, exactly. Yeah.
Okay, and in the case of MLIPs, that would be stitching the the message passing steps of one MLIP with the decoder of another.
Yeah.
Okay,
yeah,
but I guess the decoders are pretty similar, right? Because they share the same architecture, anyways.
Yeah, but they still have to be transformed into the Platonic, like the unified space first. Otherwise, all the embeddings are actually they're not aligned, right? So we couldn't
so you do that and then you freeze the entire model.
Yeah.
Okay, and you don't have to do any readaptation of anything, right?
That's true. Yeah. So yeah, that's why we can have these zero shots. Yeah, to reuse the model. So I think I can quickly go to the result, but before that, we can easily get the embedding. We define the 3 different levels of embeddings, so we can easily get the embedding of one material, right? But here we only use the mean pooling of them, of all the atomic contribution, and then get the embedding of one material, and then we can also check the embedding of we call it the symmetry difference, or because if for one computation they can have the different polymorphs, and then because we already have the embedding of each material, and then we just do the difference of the different vectors, and then we can having the embedding of their difference. And then we can also have the construct the embedding for a reaction. For example, we have one reaction A plus B to C, and then for this reaction, the embedding can be impressed as the embedding of the products minus the embedding of all the reactants. So this is where we tested if the stitch can work or not, because if we take the embeddings of all these materials from one model, then we can get this embedding of the reaction, right? But we can also do the stitching if the stitching can work, that we take the embedding of BLO from model A and take the embedding of TiO2 from model B, and then take this for model A or from the other model, and then we still calculate the embedding of this reaction. And if the two embeddings are similar, then this means that the stitching can work, right? So this is how we try to check the cross-model stitchability of the embeddings to prove that the Platonic representation can be used for model stitching in the future. But here, so we reference to all the embeddings to the embeddings get from the mass large model. So that's why the cross-model similarity of the embedding is 1, because it's to itself. And then we can see with the stitching method, all the embeddings are like quite similar, except these 2 OMAT models, but the others are still quite high. Yeah, so this means that we can do the stitching of at the embedding level. This is 0 shot, and if we in the future we train the model and align their embedding space, then we can stitch the different models.
I have a question.
Yeah.
I'm not sure I understand well. So essentially here we're saying that if we compute the embedding of the reaction with the formula you showed before,
yeah,
the cross similarity will show how much these models agree on that?
Yeah.
Okay, and so you're saying that models trained on OMAT don't agree with MACE not trained on OMAT, is that correct?
Yeah, the op models are also trained on OMAT, but they all agree well. But I'm not so actually understand, why like the 7 OMAT model and the mass OMAT model, they couldn't stitch so well.
And related to this, so I'm not sure I understand how this can be used to explain stitching. Like, why is it the fact that like these can be correlated somehow, explain that you can stitch them?
Yeah, because so the similarity is like we stitch for example, we take this other means any other model, and then we take the reactants from mass large. So this is from one model, right? For the reactants, and then for the products, they are from other models. And then if we try to get the embedding of the reaction, so if they are not stitchable, so this reaction embedding will be very different from different ways we try to stitch them, right?
Okay.
Yeah, but now actually quite aligned.
Okay, and another question is, what would be the benefit of stitching these models given they're trained on the same modality, right?
Yeah, so one very obvious benefit is, so if we want to do to get the embedding of one reaction, but actually like the TiO2 only in the training dataset, or is only accurate by the op model, but the BIO is can be accurately predicted by the mass model. So now we can combine them together.
But then that would be mostly useful if we try on different. So if we try it on, for instance, MACE trained on a certain chemistry group and orb trained on a different chemistry group, then that would be useful, right?
Yeah, exactly.
Okay, but do we know if that would transfer in that case? That would still be able to stitch them if we train on different modalities?
Yeah, so we proved that the stitchability, at least from the OP-v3 conservative model to the mass model, is 0.8. So it's quite large, right?
But I guess this is like, in that case, they kind of have similar training data sets.
We didn't only check this one reaction, we checked 20 reactions, and the conclusion is quite consistent, because
No, I agree. I mean, it's mostly that, for instance, here, if we take MACE large as the reference, it has seen kind of the same data as orb, right? Even if there might be a bit differences, it's still bulk crystals, right? And there is like an overlap in the training data set.
I see your point. Yeah. But
yeah, I mean, I guess it would be interesting to see also what would happen if, for instance, we try to train on a different data set and completely different data set. And like related to the fact that MACE OMAT is aligned differently, maybe do you know how, for instance, if we change because that might be the reason. Like if we change the way we normalize the energies, or if we change the E0, maybe that might make stitching more difficult when we train the model. I'm not sure if that's the reason why, but that could be some explanation.
Yeah, could be some explanation there.
Yeah. In which case, it would make it difficult to also stitch a model trained on different DFT functionals, for instance.
Yeah, but maybe like if we want to stitch them, we can have some deliberately overlapping data set, and then we can have like only 10% of them are overlap, but 90% are different, and then for this 10% can be used to like at least make the two data set agree.
I guess it would be difficult to have an overlap if the targets don't agree. Because, like, for instance, if we're trying to have two DFT functionals and you're trying to make the models agree, like one has been trained on PBE, one has been trained on AutoScan, for instance. And stitching is not easy by default. It's difficult to make a model train on both, right?
But I think that for the energy supervised models, they can still be stitchable, because I can show, for example, yeah, this is kind of provide some information there. So because we try to understand if the organization of this kind of representation is governed by the physics or by the training data itself. And then we also extracted the embeddings learned by the generative models. This is one of the model that trained in our group, in Aaron's group, the chameleon model. And then there's a very clear difference, right? Even though we can see the very vague organization, but still they couldn't develop this organization. So, but this is still from appearance. So we checked with one material system. This is the double well of the tin selenite. So tin selenite having the double well, yeah, in their phase transition. And then we want to check, so because we want to check two things here. One is because this potential energy surface is smooth. So if the model learned the physics, so it should develop the smooth trajectory of in the embedding, right? And then this is one thing we want to check. And another thing we want to check is because the two wells are symmetry related, even though they are not the symmetry we mean in the equivalence, but still like the two coordinates is just opposite to each other. So this means if the model is equivalent and the model couldn't differentiate the two structure, and then the model should only develop one branch of the trajectory. So that's the equivalence check. And then for the equivalence check, we found that all the mass model or 7 model or the equivalent models, they develop perfectly one branch of the smooth trajectory. But for op models, because they are not equivalent, so we can see that for the branch, they develop the two branch here. So this means even though the two structures are degenerating the energy, they should be viewed as the same, but op models couldn't like make this connection between them. And so this proves the equivalence check. And another is to prove if the physics is important. So we also extracted the embeddings from a generative model of these structures and plot them here. And we couldn't see any smoothness. So this means the smoothness and trajectory of the embedding is governed by the physics, right? Because for the math models, they are supervised, the training process is supervised by energy and forces. And so, yeah, so why this is related with the different different functionals. So what I think is the different functionals can still capture the chemistry there, but it's maybe like it's over or squeezed or stretched, or the scale is different, but we still can do some mathematical scale of them, but like the trends they capture should be the same. That's what I mean.
Right. Yeah, I see the point. But then do you think that so the mathematical transformation we would need to do to align them would be more difficult? Or like how do we
Yeah,
find essentially the way to align them? Is it like
I'm
still
not.
picking anchor points or
Yeah, I'm not sure. So the very naive check I did is for the different training data set. I checked that is kind of yeah, we can see the length here. Yeah, like the different lengths or the length of the vectors is actually around 4 or 5 times of the other models. So this is the scale that we can find or observe across the whole space.
yeah, see that for instance we can easily play with that. So if we I don't know if we extend the energy space of the targets, then that will be bigger. If we make it more constrained by taking a standard deviation that's smaller, then we'll have a smaller range for the embedding space. So I think this might be what's happening here.
Okay. Yeah.
But then it doesn't. Yeah, I think it's a bit still difficult to know how to. So there might be an easy transformation to do here, but I'm not sure what would be the right way to do.
Yeah, or maybe adding very shallow MLP layers, try to scale them. I'm not sure about the
Yeah, that's a good
techniques.
point.
Yeah.
Thank you.
Yeah. Oh, sorry.
No, I said thank you.
Okay. Yeah. So yeah, even though I explained that the non-smoothness comes from the no separation of energy and forces, but there's still one source of error I should mention is because for generative models they have their own reconstruction error. So it's worth we didn't check if all the points are still thin selenide or not, because they having their own error of the reconstruction, right? But still, we think that the main contribution to this disorder is the lack of the energy and the force supervision. But this is also provide us when thinking about the work, because currently there are some works try to align the generative models latent space with the interatomic potential learned latent space, try to improve them, and also to improve the predictability that of the embeddings learned by generative models. Yeah, so I think there are definitely some link there, but still it's not clear yet. Yeah, so another application or another benefits we observed when we have the Platonic representation is that so all the because for the math models they didn't trim the accuracy, so almost from the original space, their capability to capture the equivalence of different atomic sites between the original one and also the Platonic ones are almost the same. But we checked that because seven model and the Nequin model, they try to trim trim their accuracy. So in their original embedding, they actually are not exact equivalent, because they only have the accuracy to like the A-8 or A-10. This is like the numerical accuracy of their models. But after Platonic representation, we can help to recover partially their equivalence capability of the model. Yeah, but for non-equivalent models, no help, because yeah. So Platonic representation could not like the have the equivalence from nothing. Yeah. So another application we found is to check the models, like to check if the structure is novel or not. This is mainly related with generative models, because for generative models, we care about the stability of the generated structures, the uniqueness of them, and also the novelty of them, right? And for the novelty part, people try to check the generated structure one by one to the existing structures, and which is very time consuming. And so we think about one way called the manifold distance based metric to check if the structure is novel or not. How it works can be thinking like here. So this is the 3D map, 3D visualization of the latent space from another angle, which is actually similar to this one. But for the cloudy part are the stable materials. So the cloudy part are actually the stable materials manifold. And then all the dashed line, all the line here are the generative models. So we plot them together and put the generative materials embeddings inside this stable materials manifold. And then we divide this space or this manifold into 4 regions. So they are like the dense interior. So they're inside the manifold or can be outside of the manifold, right? So if they are inside, they can be in the dense region or in the sparse region. So, and also if they are outside of the manifold, they can be close to the manifold or very far away from the manifold. So based on the manifold theory that if they are very far from the manifold, it's kind of the hallucination of the structures. And so we try to find the novel structures inside the manifold, but not in the dense region, but in the sparse region, because for that region, which means they're still connected with the knowing knowledge, but it's less explored. So that's how we define the novel region of them. And then we use these manifold-based metrics to check the novelty of the generated structures. This can be done only 5 minutes. And then we check the different generated structures from genome, chameleon, the metagene models, and their conditioned models. And then we can see that we can have the manifold of all the atoms, right? So that's the atomic level distribution. We can also have the manifold for the materials. Materials are input from all the atoms. So we have the materials level distribution, because here for the generated structures, we more care about the materials level. And then our evaluation is very close to their own evaluation of their novelty of the generated structures, especially for this magnetic property conditioned generation. And then this is very close to the metagene's evaluation. So this means we can use this a manifold or this Platonic representation, this manifold, to check the novelty of the generated structures. And then this part is only to check the change of the structures when increasing the temperature from 0 to 1000 K. This is extracted from the OMET dataset, which is also following the trends that when the temperature is higher, then the structure will be very different from the knowing stable structures, and then they tend to be more in the sparse region, and it's kind of increasing the novelty of the structure. Yeah, so this is another application of the Platonic representation. And I think, yeah, this is the end. But for concluding that, maybe we are still in the cave, because we are in the interatomic potential cave, which the properties are governed by only the energy and force of the materials. And we can also have models on the electronic properties of the materials, or even the different modality, like the language models of materials. And yeah, when we combine the modalities together, maybe we can see the true or the more more towards the ideal reality. Constructed by Plato. Yeah, so this is the acknowledgement, and thank you very much for the questions and the attention and the chance. Thank you.
Thank you so much for the presentation. Are there any questions in the chat? Or Ali, do you have any follow-up questions?
No, I guess I'm excited to see what we can do with that next.
Okay, yeah, well, it seems like it was pretty clear to everyone. So again, thank you so much for the presentation.
Thank you.
Yeah, we'll
Thanks a
upload
lot.
the recording. Have a good day.
Yeah,
See you.
bye. Keep in touch.
Bye.
Bye.